In the name of God, the compassionate, the merciful, Engineering Plasticity, Chapter 3, Yield Criteria, Part 10. I have been talking about the yield criteria for brittle materials and introduced two criteria. One was called Moore-Coulomb model, and the other one was the modified Moore-Coulomb. We called this one the Moore-Coulomb model. We called it brittle Moore-Coulomb model, and the other one we called it modified Moore-Coulomb, or MM. Now I have an example here for you, which I'm going to apply these criterias for this problem. As you can see, this problem consists of a pressure vessel. This is a pressure vessel, a cylindrical pressure vessel. The dimensions of the pressure vessel are given. The radius of the cylinder is 20 inches. Its height is 100 inches. The wall thickness of the cylinder is 0.175 inches, and this is the load applied to this cylinder, which is 100 kip at this direction, 60 inches, 30 inches on the XY plane, and there is 100 psi pressure applied inside this pressure vessel. The material is ASTM 30 cast iron, so it's a brittle material. And what do we want? We want to find out the factor of safety against fracture for the patch using MM and BCM. That's brittle, Coulomb Moore, and modified Moore. Okay. We want to find out these the factor of safety for these yield criteria. Now, what is this patch? This patch is shown here and shown there. We have two patches, patch 1 and patch 2. Okay, that's one element. We want to find out the stresses on that element and to find out the factor of safety. And the other one is this one. Okay, this is called a patch, an element on the surface of the cylinder. The forces and the moments that are shown in this diagram are in fact the reactions to this force at the base of the tank. Okay, as shown here, the base of the tank is fixed, so this force applied here, these are the reactions. In fact, the equivalent of these forces, all of them act at this point. Okay, so the forces in fact act at these points, but these are the reactions. Okay, so we are going to find out these forces. That means we are going to find out the forces applied here and the moments applied here. In here I have drawn the reactions. First of all, we want to find out these forces. As I have mentioned here, we have these forces Fx, Fy, Fz. Mx, My, Mz are the forces and moments applied along and on the directions of x, y, z. Okay, that's x, that's y, and that's z. So Fx, because it is along the x direction, we use this force here, which is 100 kip, and so Fx is this force times this. What is this? This is cos LMN. You know, these are the cosine ratios. That's cos theta, or cos alpha, beta, gamma. LMN. Okay, 30 minus 20, in fact 20 is that bit, okay, and 30 is from here to there, so that is 30 minus 20. 10 to the power of 2, 60 to the power of 2, and 100 to the power of 2 square root. The sum of these under the square root is this line. That's 100, that's 60, that's 30. 10 to the power of 2 is that bit. 60 to the power of 2 is that bit. So it gives you this length, okay, 10 to the power of 2, 60 to the power of 2 is this length, and then that is the length we want, and that's 100. So 100 to the power of 2, and that length to the power of 2, which is 60 to the power of 2, 10 to the power of 2. So that is the cosine alpha, or L times 100, gives you a component on the x-axis, which is 8.54 cube. And also Fy similarly is L, that's L, that's M. 100 times cos beta, that's 51.26. You can work out this, for instance, that is 60 over this, because that's the line, okay. So every time we want to find out the direction cosine, we must use the relative length, which that is in the y direction, that's in the x direction. So that's 51.26 kip, and that is 85.44 kip. Okay, so in this way we have found out the components of these forces along x, y, z direction of this force, component of this force along these directions. Okay, now we are going to find out the moments, okay, moments of fx, fy, fz about xy and z axis. Okay, so mx is the component of the y axis, f about the y axis in the direction of the y axis about x. Okay, so that is 51.26 in that direction times 100 inches, it becomes 5126.1 kip inch. And the moment about the y-axis, we have fx and fz, fx and fz like that on this patch, and so we have this 8.54 times 100 inches, because that's the 100 inch. So we want to take it about the patch. Okay, and my, look at y, we have this axis y, so we have one component of fx and one component of fz. Okay, and so fx times 100 inches, that distance, and z 85.44, we have that distance, which is that distance, because to the patch, up to the patch. Okay, z direction up to the patch, that's the reaction here. Up to the patch is times 20 inches. Okay, so it becomes 2562.8 kip inch. And the moment about the z direction is this. Therefore we only have the forces in the y direction. About the z direction gives the moment mz, and that is 51.2 times 20 inches. Again, here we have fy times this, okay, times this, because that's the z direction, and we get 2 inches. Okay, so fy times z for the patch. Okay, is acting. We want to find out mz for the patch. Okay, so that's 1225.22 kip inch. These are the moments and these are the forces. Okay, so these are all of these are the loads caused by this force, 100 kip force. Axial force due to force Fz, which we obtained just now. Axial stress due to Fz, which we obtained now, is given by sigma A is equal to Fz over the area, which is pi r squared. Okay, and here we get sigma A equal to, the force is of course negative because z direction is in that direction, that's the reaction, so we get the negative force here, that's a compressive force, and sigma A therefore is minus 85.44 kip, and this is the area. Okay, because in here I wrote it in general. What is this? This is 20 inches is the radius, and 0.175 inch is the thickness, so that's the outside radius and that's the inside radius, and that is the area, so that's minus 3902.27 psi is sigma A. Now on this patch in here we can draw the forces, so the stresses, so we have this stress which is a compressive stress as shown here on patch 1. Now again here we have the moments such as my, which is equal to 2562.8 kip per 8 kip inch, and the normal stress due to bending is given by this formula, which is sigma n mc over I, and substituting the values, m is again negative, my is negative because we usually take the anti-clockwise as positive and clockwise as negative, so this is negative, and we put it here, minus 2562.8 kip inch times c. C here is equal to r, and that is I. Okay, that is the diameter of the cylinder, outside diameter of the cylinder, that's the inside diameter of the cylinder, so that is the I for this cylinder area, which is minus sigma n is minus 11,807.9 psi, and on this patch we had this stress before caused by forces in the z direction, and this is the normal stress caused by the bending moment. So we have both these forces acting on this patch, okay, because we want to find out the factor of safety for the patch. Okay, then let's go further and find out about the internal pressure. Now also in the z direction we have this internal pressure, because at the beginning of this problem we said that we have 100 psi pressure inside the cylinder. So the stresses caused by the internal pressure are in two directions, one in the longitudinal direction and one in the hoop direction, okay, circumferential direction. So sigma L in the longitudinal direction or axial direction is PR over 2T, and P is 100 psi, and R of course is 20 inches minus 0.175, that's the internal radius, and divided by 2 times 0.175 inches, which is this, and we get here 5,664.3 psi is the stress, longitudinal stress, due to the internal pressure. Therefore, this is the axial stress in the z direction which is applied at our patch. So as you can see, the direction of this one is positive. Let's see if we have other forces acting on this patch. Obviously, we have the stress due to internal pressure in the circumferential direction, okay, hoop direction, circular, circumferential, and so sigma h. Hoop is PR over T, and again, internal pressure is 100 psi, and we put these in here as well, and we get 11,378.6 psi is the hoop stress that we have here, and therefore we add this hoop stress as well. Hoop stress on the patch, okay, on the patch in the circumferential direction is like that. So these are the stresses acting on the patch 1. Here the torque is mz, that is this because the torsion is caused by such torques or moments like mz, so the torque or mz is 1025.22 kip inch, which we obtained in previous slides, and therefore we substitute here for P over 32. This is for the circular section. For the cylinder, J has a standard formula, and obviously here we have substituted for mz for T, and C is equal to the radius, so we get 2361.8 psi is the shear stress, and so we have put the shear stresses here, okay, shear stresses here, and so far these are the stresses acting on the patch. Another component of the shear stress is due to the transverse shear forces, okay. So the transverse shear stresses due to bending are given by this. Tau transverse is equal to VQ over IT. V is the shear force due to bending, and Q is the first moment of area. And for the circular section is given by dq over 12 for such a patch in here, because it's situated on a semicircle. So that's d cube over 12, right? And also V is equal to the shear force. In here, shear force is in the y direction and is equal to the 51.26 kip. Therefore, the transverse shear stress tau transverse is equal to the shear force, which is 51.26 kip here, and we got d cube here because it is a hollow circular section, hollow circular cylinder. Then we put the outside diameter 40-inch cube divided by 12 minus the hollow section, which is 40-inch minus 2 times t to the power of cube divided by 12, and this is the value for I times the thickness of the cylinder. So we get here 4,682.3 psi is the transverse shear force, which we put it on the patch like this. Okay, so we got all the shear forces and the normal forces on the patch. Here we are computing the component of stresses. Therefore, we add all these stresses in the z direction, which is these three stresses. We get 10.05 ksi minus, because it's compressive, this is tensile, this to compressive, the magnitude of this is greater than this. Therefore, we get 10,000 psi compressive stress in the z direction. In the y direction, we have only this stress, which is 5664.3 psi, and we add up the shear stresses and we get this. Now, in the principal stresses on the patch, we should obtain them from the Mohr circle. Therefore, these are the principal stresses, sigma A and B, sigma x plus y over 2 plus minus the square root of sigma x minus sigma y divided by 2 plus tau xy squared. Now we have obtained all these values for sigma x, sigma y, sigma and tau xy in the previous slide, and we add them together. Okay, so we put them all the values in here, and therefore we get sigma A equal to 13.49 KSI, and sigma B is minus 12.15 KSI. These are the principal stresses on the patch, and therefore we are going to compute the factor of safety for BCM, that is the Mohr circle, Mohr Coulomb model for brittle material. And here we are. If we have put this in the formula, and that's the factor of safety. These are the stresses, and so stresses, and these are the stresses we obtain, and these are the tensile stresses for the material. As we said, the tensile stress in tension and compression are different. That's why we got these two values in here, and therefore we get 1.83 is the factor of safety using brittle material for Mohr Coulomb model, and MM is the modified Mohr Coulomb model for brittle material, and for that one we get this value, which is 2.29. okay, and we are now going to draw the yield criteria and see where the load point is, and make a comparison between the two yield criteria. Now this was the modified Mohr Coulomb model, and this is the Mohr Coulomb model. So we call this BCMB for brittle material, and this one of course is for brittle material, but it's modified more. We just call it briefly MM, and this one BCM. And for this one we've got 1.83, for this one we got 2.29, and our torsion or pure shear line is this, and this is our load point, okay, sigma A and sigma B. In fact, from here to there is sigma A, and from here to there is sigma B, which is 13.49, and this is minus 12.15, and this is the load line. Okay, as you can see, for the MM model, which is this one, sorry, for the MM model, which is this one, is further away, and so the load line could go up to there before yielding, and we have this is the load point. So this line divided by that line gives 2.29, and for the Coulomb or BCM we get this, okay, this one, which is this line up to here divided by the load, which gives us 1.83. okay, and if we increase the stresses we get up to here, which is the yield point. Now then, let's see how to choose the yield criteria. How do we choose which yield criteria? Mises, Tresca, Coulomb Mohr, or modified Coulomb Mohr? Which one? First of all, we consider whether the material is brittle or ductile. We answer this question, okay? So if the epsilon or the strain is greater than 0.05, we say it's ductile. And if it is less than 0.05, we say it's brittle. So if it is brittle, then we must decide which criteria we want to use, more conservative criteria or closer to experimental data. So if we decide on that, for instance, more conservative, we knew that is BCM, which is Coulomb-Moore criteria for brittle material, and this is modified Moore criteria, which is closer to experimental data. Now, if the material is ductile, then we say that whether it has the same yield strength in tension or compression. If the answer is no, then we use the DCM, which is the Coulomb-Moore criteria for ductile material. And if the answer is yes, the yield strength in compression and tension is the same, then we either use Tresca or Mises, depending whether we want to be more conservative or closer to experimental data. So this flowchart could be used in design problems.